All right. Welcome. And we are live coming at you from sunny Palo Alto here. We're back in the office, I know, which is a shocker. Makes you wonder what year this actually is. All right. Well, let's wait a few minutes for everyone to trickle in. Anyone that's joining us already, a few key steps here. Number one, on your chat in the lower right, make sure you change it to panelists and attendees. Otherwise, you're just going to be pinging us the whole time. So change that. And please go ahead and put in the chat, introduce yourself. And we would love to hear, what is the first product that you ever tinkered around with or tore down? Yeah. So I'm joined here by Chris. Maybe Chris, do you want to share what your first teardown story was?
Yeah, I think my first introduction to consumer electronics and as an industry that I could actually work on was through an internship at Palm. And my job was actually to tear down products for a competitive benchmark system that they were trying to put in place. So I tore down a bunch of phones, but the first one I tore down was actually a Palm Trio, because they wanted me to understand what their products look like first. So that's kind of how I got hooked into this industry. And from there, since then, I've been part of it ever since. How about you?
Awesome. The Palm Trio. Wow, that was a ways back.
It was.
Mine, kind of the first unofficial teardown, was actually the original Xbox One. If you remember, giant black box with the green logo.
Yes.
I don't even know how many years ago. I wanted to install a mod chip. And for those of you that might not remember, this was big back in the day. You could mod your console, which would allow you to install third-party software, third-party operating system. It's kind of bypassing the Xbox security. And back then, you couldn't even do it with software. You had to install a physical chip. So I ordered this chip off of eBay. God knows where it came from. And to install it, I had to tear apart the Xbox, desolder a few joints, scrape off a few connections on the PCB, and then clamp down this third-party chip to the main board. And it was a very difficult process. I did finally get it to work. I would not recommend trying it today. Even to this day, I still have that Xbox. You have to bang on the side a little bit before it actually turns on properly.
That's an awesome story.
I know. Did you remember modding of consoles back in the day?
I do remember. I mean, hardware mods is it's so hard now with everything just soldered directly to the boards and basically glued in place. But yeah, back in the day, I totally remember people doing that. And yeah, it's just how things have changed.
And that was before the days of iFixit, where there was a well thought out teardown of every device that you could find online. This was like searching through the deep web, trying to find someone that had done this before. All right, welcome to all the newcomers joining in. If you haven't already, reminder, switch your Zoom chat to panelists and attendees, and then introduce yourself. And please post what is the first product that you ever took apart or tinkered with. And
it looks like I'm getting quite a few people in here now.
Yeah, they're flowing in. I think we're almost ready to get started. The other probably the first official product that I tore down, the Xbox, that was way back when I first worked at Apple. It was the iPhone 5S. But the first Touch ID sensor, which was a huge deal back then. Fingerprint reading was in its infancy.
Yeah.
And we did lots of teardown. And the funny thing was we bought iFixit kits because we didn't have enough tools to actually do teardowns of our failed devices.
I also purchased an iFixit kit when I was at Amazon because you can't beat them. They're pretty comprehensive and they're perfect for taking apart all the competing electronics.
Yep, props to them.
Yeah.
All right. Excellent. Well, let's go ahead and get started. So welcome everyone to Change Notice. This is a weekly video podcast where we discuss all things hardware, electronics, manufacturing, hosted by product design engineers, mechanical engineers, with the purpose to build a community for knowledge sharing, support, and continuous improvement. So normally these are hosted by our CEO, Anna, but today's special unsnapped teardown is hosted by me, and I'm joined by Chris as well. We'll give you a little more intro in a minute. Quick reminder, if you do need to duck out early, please fill out the short survey at the end to give us a little bit of feedback about what to talk about next time. Again, reminder for newcomers here, change your chat down in the bottom right to attendees and panelists and tell us about yourself and first product you tore down or first product that you worked on. Excellent. So let's start out with some introductions. I'll kick us off. So I'm Tobias. My background is mechanical engineering. I did product design for about 6 years back at Apple. I worked on 4 generations of Apple Watch, focusing on the heart rate sensor, the ECG sensor, and then also 2 generations of iPhone, working on touchscreens. And we also want to share just a little about what got you into mechanical engineering in the first place. So again, for participants here, would love to hear what was that experience that first got you into mechanical engineering or product design. Mine was a combination. Growing up, I did a lot of woodworking, construction. My dad had a handyman business. I really enjoyed building physical things. And then I also got really interested in building computers. I wanted to build a gaming computer. That was the hot thing at the time. And the combined interest in electronics and building physical things is what drove me to mechanical engineering. And I'm joined here by Chris. Chris, want to introduce yourself?
Yeah. Hey guys, I'm Chris. I worked at Amazon kind of right when the first Kindle came out. And I worked on maybe 4 or 5 different versions of the Kindle, from the Kindle 2 to the Kindle Oasis. So those were all my babies, and took a lot of time and effort and blood, sweat, and tears to get those out. More recently, I've been working on a health tech startup and doing some mechanical and other work for them. How I got into mechanical design, actually, my brother, my father, my grandfather were all electrical engineers. So when I went to college, I was like, I'm going to become an electrical engineer. I took the first core classes and I was kind of struggling because I just couldn't quite get through the concepts of like how all these like digital signals were going. And as a break, I took a class in, I think, fluid mechanics. And I was like, whoa, this makes so much sense. I can do this like just turning on the faucet and seeing how things work with my hands. And took some shop classes, got really excited about mechanical design. And then, as I mentioned earlier, I got that internship at Palm and got turned on to consumer electronics. So that's kind of how I got into mechanical design.
Excellent. Well, thanks for joining us, Chris. We've got an exciting session ahead of us with some fun hands-on teardown.
Yeah.
So agenda for the time we have here. We thought, the best way to really understand a product, you got to tear it down. You got to take it apart. So we're going to do a live teardown of the PlayStation 5 controller. But we're also going to discuss and debate some of the design decisions that Sony had to make during the development of this. And then towards the end, we'll also have a live Q&A session where folks can come up, ask more questions, and we can get a little more interactive. So I'm super excited here. The button mechanism is particularly exciting. So they got some pretty clever designs. So let's just dive into it.
Yeah, so this is the PlayStation 5 controller, and we decided to take this one on because you might have heard a little bit about this in the news recently. I think it just came out maybe towards the end of last year for Christmas. But you know, there's been some really cool technology that they've added to like have these triggers that kind of fight you, they put some cool motors in there, but also they're actually, I think, facing a class action lawsuit against like the joystick drift. And they're not the only console maker that's facing this. I think Nintendo is also facing a lawsuit with this. So what is up with this? Why can't these big companies fix this kind of issue? You know, they've been making these controllers for forever. So we're going to dive in and see if we can at least see what they're dealing with. So this is my screen here. I can turn it around. So controller. I think the first thing to do is actually to take off this black plastic piece here. And I got my trusty little spudger tool. Just got to go in, kind of unsnap some hooks here.
So are there no visible fasteners on the outside or screws?
There are no visible fasteners. That's right. Yeah. So I think they did a pretty good job with hiding that. Like I have an Xbox controller here. It's got, I don't know if you can see, there's like big holes that have to go through with some snaps or some screws, but this one basically is all snapped together. So I'm going to switch to this plastic one here. So a couple of snaps in, and they're actually taking advantage of the fact that this plastic piece here is a little bit flexible to basically snap it in place. Let the camera refocus on this. Yeah, and there's a lot of snaps in this little plastic part. So I think I counted like 14 different undercuts in there. But once you take that off, I think you also got to take off these buttons. So there's two buttons here, the trigger button that we're talking about, and then this upper button, which really just pops off, and this might go flying. And this other one might also go flying. There it goes. But it just exposes, there's two screws up here, and there's two screws down here. So I'm going to take those apart.
What's the screwdriver you're using there?
I'm using a PH00. All the screws I think in this product are actually Phillips. So it's pretty simple. All you need is a single regular Phillips screwdriver.
That's that was very kind of them thinking about repairability. I'm sure the guys over at iFixit would be happy.
I think they would love that. And I think a lot of people have been opening these to kind of get inside and try and figure out what's going wrong with their the drift in their buttons. All right, so I got the 4 screws out. There are these 2 little hooks here that you got to take off, and then basically this whole bottom casing will come out. So I'm just going to lift that up, get it over the edge. See if I can get that there.
I see Taylor's pretty excited about the ease of repairability here.
And there it is. So we got the device apart. Let me put that back in the center. So looks like we got a hard case battery here, which is pretty unusual in consumer electronics. I think, you know, there's also quite a few little connectors. Looks like there's maybe 5 or 6 different flex cables in here. Maybe we can ask the audience what they feel like, what they want to talk about next, battery or these connectors. And maybe while we're doing it, I can take it apart a little bit further to see the rest of the board.
Yeah, both of those look pretty interesting. The battery came out pretty easily. So no adhesive.
No adhesive. There's a little foam piece here. I guess they're probably maybe compressing against it to keep it in place and hold everything down. But yeah, it's pretty solid plastic covered battery. I haven't seen these since like the cell phones before they were smart. Like you could like take those apart. So it's an interesting, curious decision, but maybe it was used for sort of robustness, just because these controllers could be thrown around a little bit, or maybe there's maybe they're worried about the cell expansion and they want to keep this, keep the case compressed. So they wanted to kind of distribute the load against a more plastic case instead of the bare cell packs that you might find in like an iPhone or a Kindle. The only other thing go ahead.
We've got let's see, a few questions coming in. How is the battery attached? I think it was not adhered, and it was just kind of a press fit into that cowling combined with some foam on the top, right?
That's
Chris?
right. Yeah, I think there's it's not even that snug of a fit. It just kind of sits in there really. And then it's basically just compressed with this foam, and it's got what I would call like a Molex connector, just a press fit connector on the other side.
Yeah, that's really interesting. The hard shell, that's definitely unique compared to a lot of the other electronic devices that I've seen. Again, normally when you're going with just the soft cell lithium ion pack, it's to save space. So I think they probably had extra space. It probably also adds a layer of protection for handling as well. I know from instrumental customers, actually, we've had mobile phone customers where there's a lot of screws around the battery on the main PCB, and they end up getting dented. The batteries get dented when operators accidentally poke them, which is pretty dangerous for those lithium ion packs. That was one of the things that we were catching a lot of for some of our customers. So the hard shell, not super space efficient, but it's going to prevent that, and probably a lot easier to swap out as well, because there's no adhesive. When you're tearing down phones, it's always a risky maneuver to pry up that adhesive.
Yeah, I think that makes a lot of sense. I mean, given that they have the room for it, might as well make it as simple for their operators as possible and protect them, so that there's no battery punctures when people accidentally throw them against the wall when they're frustrated with their game.
Yep.
Yeah, cool.
Great. Let's see. We've got some requests on the connectors and termination type. I think on the main PCB, we got a few questions. Just again, note for all attendees here. A lot of you guys are sending messages just to the panelists, which is fine, but it's even better if you switch the little blue dialogue in the lower right to panelists and attendees. Also a question on the battery capacity.
Yes, the battery capacity looks like it is a 1560 milliamp hour battery at 3.65 volts. So it's a 5.7 watt battery or watt hour battery. So that's pretty standard for, I think, consumer electronics. I remember, I think the original Kindle I worked on had about a 1500 milliamp hour battery. And I think actually some of the iPhone batteries might be even bigger, but they're in a smaller package now. Any other questions about that?
Let's keep going. And I think there's some interest in the connection type for all those other connectors. So let's look at the main board.
Yeah, so why don't I take off this little battery cover, or kind of cowling, as you mentioned. Oops, and forgot to take off, this was a little microphone. But yeah, looks like they're using a lot of what I would call LIF, or low insertion force connectors. I was used to a lot of like low Z-height ZIF connectors, but these actually all stick almost entirely straight up. And actually, it's a little hard for us to see here. So I was wondering, maybe, Tobias, if we can zoom in using the instrumental platform, maybe we can switch over to some pictures that you took earlier.
Yeah, let me pull it up. I think you'll have to stop sharing
There you go.
for a second. Bingo. And so here we are. So we actually have some high resolution photos in case Chris's webcam isn't quite enough. These are in the instrumental application. For anyone that's not familiar, Instrumental is a software platform, and we aggregate data from assembly lines. And a lot of this is image data as well as test data, make it accessible in our interface, and also do AI analysis on top. Today, we're just going to use it to look at some images with the interface. So this is kind of the state that Chris had it at. And we wanted to look at these connectors here. So we were talking about these low insertion force, which is pretty interesting. For most of the devices that I worked on, we used a lot of some zero insertion force, some ZIF, and some board-to-board connectors. So you can see here, this is going straight down. It's a flex ribbon cable with a little stiffener on it, and it just press fits down and makes contact. I think there's two here. And then even over here, here's a larger one. And it has this large pull tab, which actually makes it easy to pull in and out. And I've got a few thoughts on why they might have chosen these over maybe the more traditional ZIF or board to board. I know ZIF connectors that have the latching mechanism after you put in the flex and clamp it down. Those are a little bit more expensive, a little bit more prone to cycling wear. If I think most of them are rated to just about 10 cycles. So if there's any type of rework, any type of repairs or replacement of these parts, they're at much higher risk. And I don't think space was an extreme concern here. What else do you think, Chris, led them to use these lift connectors?
Yeah, that's a good question. I mean, I think you covered a lot of the bases there. I'm trying to think if there's anything else that, actually in this vertical orientation, I think it would be actually pretty hard to find a ZIF that kind of locks in that orientation that they could get a solid clamp on. So maybe they were restricted on some of those just because of the way the parts are coming in. Trying to think if there's, and it makes it easier to assemble for the operators if you're just pushing straight down, kind of getting a gravity assist as well, and not having, I think we used to have like plastic tweezers that have to put them in place, and then they have to flip the little covers down on some of those ZIF connectors. So yeah, maybe that's another.
Yeah, another good point by Michael that you were just bringing up. Not only ease of repairability, but ease of assembly. Like it's just super easy to push it in. Question from John on if the connectors, are they backed up with a pad? I don't believe so. These are, again, there's a stiffener on the flex, which is what you can see here, kind of pointing out of the screen, and it's press fit down vertically. And there's a spring force within the LIF connector that holds it in there, but there's no additional force holding that flex in. All right. Again, keep the questions coming, and let's continue tearing this thing down.
Cool. So I think to get at the next part, I'm gonna have to remove some of these connectors, and then I can flip out the board and we can take a look at what's underneath. So that just pulls right out.
It's pretty easy. We got a question from Parth on what to do if FPC tends to slip out of a ZIF. Are lift connectors better? From my experience, ZIF connectors actually have a larger clamping force because they actually have the lever mechanism. So I don't think that switching it to the lift is going to solve that issue. I would probably double check the flex thickness, maybe measure the actual OQC of those flex parts. We've had issues before where flex thickness was not coming in at spec. You have your stack up for your flex, but that's not what's actually being made. And so if your flex is too thin, then the ZIF connector is designed to clamp some nominal thickness. And if you're out of that bounds, then you're not going to get the clamping force that you want. All right, what do we have, Chris?
Yeah, so we're looking at a couple of interesting things here. One, I don't know which way you want to see this, but this, I just took off little caps from the analog sticks. These are the infamous analog sticks. Something else that's pretty interesting is you can see there's this other flex cable here that I think goes to the button flex on the front, and there's no actual connector for it. It looks like they're just kind of traces from that flex going directly onto the board here, which is pretty cool. You can see some of these, there's 4 motors in this product. So I think 2 on each side. I'm trying to see if you can see this. There's one big one here, and then there's like a little silver one here for that trigger mechanism. So yeah, there's a couple of different things that we can talk about. Next, maybe, yeah, do you guys want to see a closer look, take a closer look at these analog sticks, or you want me to open this further and see the see how the buttons work on the other side?
Or if you've got anything else that catch a glimpse of in rotation there, just post it in. This
in
is
the meantime, I'm gonna take out a couple more screws and just get it to an easier state.
Yeah,
but yeah, just let us know.
I see a few requests coming in on the joystick.
Okay.
Let's see. Are you able to get a close up of that? Otherwise, I'll pull up. Why don't I just pull up?
Yeah, why don't you pull up yours? I think it's going to be hard for people to see on my screen.
All right. So we tore it down. Let's hop all the way to the PCB here. You can see we've got the full assembly. So this is what we're looking at. These are the joystick input components, the infamous ones that have been wearing out a little bit too early and causing this lawsuit. And you can see on the back side, just taking a look at this PCB as well, it looks like these are through hole soldered. You can see here, those line up right here. Through hole soldered with all these pins here, and then there's a few hand solder joints that look like they're connected to the vibe motors over on the side. Taking a first look before we get to the actual wear and tear and why those are failing early. Looking at these solder, you can immediately see there's this residue on both sides. Likely from the post SMT. This looks like a through hole solder process, but this here doesn't look great. This looks like
it looks like a cold solder almost. Like it's balling up and it didn't wet out.
Yeah, and then the damage, the surrounding little burn marks. Look a little bit concerning. Again, this is something that we see a lot with our instrumental customers. Something that's not always caught by their traditional AOI system, and just kind of looks a little bit off. That might be an indicator of a process drift, even if it's not failing yet.
Yeah, I think another thing, like I see like the motors are kind of hand soldered on here. Oftentimes those things aren't quite soldered properly, or they're doing it really quickly. I guess, is that another thing that instrumental could find if there was like a lot of variation through that?
We have had a lot of success with hand solder applications, or rather inspecting and catching issues on hand solder applications, because as a product designer, I would avoid hand solder at all costs, if at all possible.
That makes sense.
I've not seen a good way to make that process repeatable.
Yeah, I think that's pretty hard, but I also think it's pretty hard to get, I guess you'd have to put another set of connectors on here for those motors if you're going to do that.
Yeah, I'd be curious from the audience. Again, thinking about these joystick components wearing out, and we're going to talk about some hypotheses why. Would there be a better way to design this board to actually make those swappable? Because right now, these are not repairable at all. They're soldered directly on the board, whereas the rest of the device, it looks like the battery, the connectors, the motors, those are all designed to be pretty easily repaired. So if you've got ideas, post them over in the comments. Let's look at these. Let's look at these components. What do you think we have going on here, Chris?
Yeah, I mean, it looks like I think these are really interesting kinds of connectors. I think it's like two potentiometers, so they're basically going sort of front to back and side to side, and you can move this joystick in any orientation. And there's probably some wiper blades in there that are detecting kind of where the component is in space. You can also see, I think right under the bottom of this picture, there's like a dome switch as well. So they're using, like, when you press on the center button, you're also able to make another contact. So I think a couple of people have taken these apart even further, and there's like, I think there's a spring that pushes them up. So maybe something's going on with that spring. I don't know. What do you think?
Yeah, I agree on the design here. It looks like two potentiometers combined with a single axis spring in both orientations here. I would be suspect of the total cycle life of those springs, just thinking about the amount of use that one of these things gets, and the manufacturing variation of these plastic parts. Some edge cases definitely seem like they could wear out earlier rather than later. And then inside as well, that electrical wiper connection, again, that seems like that's probably going to be a pretty critical connection. Yeah. And you would need a pretty good safety margin, design margin, to be able to cover all cases for nothing to fail early. I do wonder if they had the proper reliability tests and cycling tests in place to catch this early on. If they knew about it through testing and this was a known risk decision, or if the quantities that they tested during their development builds were not large enough to get these outliers of either assembly or part quality. What do you think, Chris?
Yeah, I mean, I think it could be a combination of all of these things, right? First of all, you're going from maybe 100 to 1,000 to maybe 5,000 build units to like 5 to 10 million of these. I think they sold maybe 4.5 million consoles, but there's maybe 4 times as many of these joysticks out there. Just, you don't really want to play PlayStation 5 by yourself all the time. So you got to sell more of these controllers, and each of the controllers has 2 of these joysticks. You also got, so the manufacturer, I think it's Alps in this case, is ramping up their production. So there's going to be a wider, maybe tolerance variation there. And maybe you didn't see it. Maybe you're testing, like if a robot is testing this instead of a human, sometimes it's more controlled in how those are tested, and not necessarily, someone jamming on the button all the time, like to the max. I know sometimes when I play games, it's like I'm really frustrated that my character isn't going to the right, and I really want him to go to the right, so I'm going to jam on that button, and that could make it a little bit wear a little bit faster.
Yeah, that's an interesting point. Is I would hope that they had a proper reliability test set up. Again, that's one of the critical things in designing a robust product is the reliability suite that accurately represents real world use cases. And I cannot emphasize that enough. It can't be just a fake test. It has to somehow correlate with the real world life cycle. So I would hope that they had some type of automated cycling test for this. But to your point, we also found in the past that we were designing an automated button press for iPhone button cycling, and an automated fixture with the same exact orientation was not the same as a real world use case. And so we ended up adding another test, which was an operator pressing it because the angle, the tilt, the force was varied enough that that was a significantly different test.
Yeah, I had something similar on the Kindle. I think the Kindle Touch. I had a really small space to put the USB connector in. We had the, the USB connector. The vendor's like, yeah, insertion test, 10,000 cycles, it's fine, right? And then, we added a test to do a manual insertion, and people are kind of putting it at a random angle or something like that, and it failed after 2,500. And so we're like, what's going on? The vendor's saying it's 10,000. The machine says it's 10,000, but we're only getting 2,500 cycles out of the human test. And sure enough, like something was cracking inside. So, it's definitely, we're not machines, and so we got to get to that real world testing, like you said.
Yeah, we had to come back. We had a few comments come in here. On, let's see. Kieran's asking, how would they set the input force for the reliability test? That's a great question. There are many large reliability teams that spend a lot of resources trying to map the real world use case to often an accelerated reliability test, often through some type of designed experiment and data collection. So one thought would be to set up some type of input rig where they actually ask a user to play a game, get a sample set of users and measure the force, have a special setup that's actually measuring the force input into the joystick here, collect that over X number of users, add a buffer, of course, because you always want to test to extremes, accelerate the life cycle, and then use that as a starting point.
Yeah, I just wanted to point out, I think Taylor sent out a whole article that iFixit wrote. So Taylor, I think you're from iFixit. Thanks for sharing. I think that's, we got a lot of information from that. It was really cool how they took the whole thing apart down to like the parts off of the ends of the potentiometer and opened up the spring. So you can take a look. They got some great video and some pictures in that one. So thanks for sharing that. That's awesome.
Yeah, and I think Taylor's experience here is really, he's got the perspective on Nintendo's as well. He dropped some knowledge that the Nintendo, back on the repairability, Nintendo's joysticks actually do provide a much easier swap out. It sounds like there's just a single cable and a ZIF connector.
Okay.
A little more thoughtful design for swapping those out.
Yeah.
All right, a few more questions before we move on. I do want to get over to the buttons. Those are pretty cool, and the trigger mechanism. We had a question on the IMU placement on the PCB, design decisions there. Let me find that. So let's look at the main chips on the top side. Most of these, from my experience, the placement is driven by a few key factors. One's going to be routing of all the traces to wherever they're connecting to. Most of these look like they're connecting to different these low insertion port connectors to go off to the buttons, the motors. Yeah. So routing is probably number one. Thermal management, if they need to. I don't think that these chips were actually making contact with any thermal pads to dissipate heat. So I don't think heat was a concern here. So space on the board. I don't think interference in Z was a primary driver in these designs. I know that's a big one for tighter consumer electronics. But for this one, I'm going to go ahead and say that efficient routing, and again, that's not just where do the traces fit, it's where do they fit while not having, there's a multitude of different crosstalk, electrical interference that can happen when traces aren't laid out. This is what all the electrical engineers in the room probably know better than I do.
Yeah, I think it looks like I think I looked up that big chip there on the right, and I think that's their proprietary chip. So I think that's what's controlling the motors. So it's probably like a couple of bridges maybe for the like turn on the motors and keep them on or put them at different frequencies. So that's a lot of power that's going in, and you can see the big fat traces that are going to that one. Also, I think if you look down a little bit on the bottom, there's a space that's kind of completely empty. It looks like. I think that could be an antenna trace. I think it connects via Bluetooth. Maybe. Looks like that could be like the 50 ohm line there. So you know, it's kind of in this case, it looks like they had quite a bit of room to do things, but you know, like they got to separate out those joysticks, which are going to get put under a little bit of load, and then they wanted I think the optimal routing for like where to put the power hungry components in is probably what dictated a lot of the placement for these components.
I thought maybe one more thing before we move on. Not shown here, maybe it's on the other side. I think there was a small speaker module that connects right on top of these two spring fingers, but there's no other physical connection holding it in place. It's just sandwiched between these two springs on the main board, and then the front cover, which I thought was pretty clever.
Yeah, I think that makes it a pretty simple component for assembly and easy to replace. You know, that's one of the few places where you could get some water damage potentially into this. So if you needed to replace that speaker, they could just get in there and swap it out.
Let's go ahead. I know before we're asking trigger module buttons and the joysticks. We got some requests for the buttons.
Okay.
Let's continue tearing down.
Yeah, so I think the buttons are one of the most interesting things about this the controller, just because you know, it's a very unusual layout in the buttons here. The domes look a little different than normal. And actually, I'm kind of kidding here because there are no domes on this button layout. This is just a flex, and you can see it's just very thin. There's no, it's like carbon ink or silver ink that's placed on here. What's it? Yeah, go ahead.
I want to know. I'd love to hear from the audience. First reaction when you see such a simple flex just laid out like that. And Chris, if you want to bring back the other half, the front half with the buttons, I was puzzled for a second trying to figure out how the button mechanism actually works, because I expected some simple dome switches. Any ideas from the audience on how those buttons work?
So here's this, like, basically there's no connector. You can see it's even etched away from the board, and then there's a flex on top that just sandwiches in there with through-hole connection.
Yep. We got a suggestion from James here on I think force sensitive resistors. Good idea. Could be resistors on the flex that react and change resistance to pressure. Taylor from iFixit here is saying he's still stumped on the buttons. Well, we've got a hypothesis for you from a little digging.
Yeah.
If you can kind of show the close-up of those white, we might need to hop over to the app, but you've got those little black buttons that depress and make contact. Let's see, Karen's asking for the actuator buttons. What we actually did, we took a multimeter and measured those black buttons that those ones right there that are making contact with the flex, and they're actually conductive rubber. And so we're pretty sure how this button works is the flex just has an open circuit with two pads. And then as the conductive rubber makes contact, it closes the circuit to make for just a dead simple button press that has no mechanical parts to actually fail in it. And so that's pretty clever.
Yeah, I thought that was a really great solution. I think it also, we were looking up this, the PS2 and 3 controllers actually had force, like sensitive or sort of tracking. I guess you could like press harder into the button and get a different reaction. So I think that might have been a holdover from this. The other thought that we had was this is a really simple mechanism, and these buttons might get millions of cycles, and typical dome switch is maybe 1 to 5 million cycles. And if you want to make sure that your button never fails, make sure there's no mechanical part in it. And so, you know, if you do a quick calculation, you can get maybe like 10 to 15 million button cycles in a 5-year life cycle of a controller. Something that doesn't have a mechanical switch in it is probably going to last as long as you need it to. You can see there are actually a few dome switches on this controller, but they tend to be for buttons that are a little less important, like your start or your menu button or your create button that are not used as frequently, or the reset button like on the back here. So, you know, I thought there's interesting choice from Sony, and I think it's pretty well done for this.
Yeah, we've got a question from John. Yeah, I think to your point, Chris, and to a couple other comments coming in here, that the reliability and the life cycle with this design is just going to be much higher, much simpler. No mechanical components to fail. Question from John on, does the resistance of the rubber change? Chris, if you stop sharing for a second, I'll zoom in on my side just so we can take a look. Does the resistance change as you press down more? This is what Chris was alluding to. So we have these rubber pads here. And yes, sure enough, as you press down more, you get a lower resistance. And the likely design here that I've seen a few times in the past is it's probably a bulk non-conductive material that's impregnated with silver particles, silver ink. And if you get the density right, then you get the kind of nominal resistance. And then as you compress it more, the distance between the particles goes down and you get less resistance. So in theory, these buttons, like Chris mentioned, are pressure sensitive. Based on the resistance there. Sounds like PlayStation and Sony, they're not actually using that feature for this controller. I'm not sure if that was a hardware limitation or just from the feature side, they decided it wasn't being used enough.
Yeah, it looks like Michael is saying that this used to be used on 80s and 90s calculators. I would say of all the big tech companies that made calculators in the 80s and 90s, Sony would have been one of those that probably had a division doing that. So, you know, kudos to them for making something old new again and really figuring out how to make that work.
You can see here just a close-up of...
Oh yeah, it's a great picture.
Yeah, close-up of these two conductive pads that the buttons make contact with. Again, just dead simple flex. Interestingly, on the right-hand side, the non-directional buttons, these look like they have a slightly different pattern on the conductive receptacle. It still looks like just two traces, but our best guess here is redundancy for any kind of angular pressing of this button to make sure it's still registered properly. And you can see where the flex connects to the PCB that Chris was pointing out. Again, this is another dead simple design, kind of reduced complexity, helps out in a lot of scenarios where that flex from the buttons, it just makes contact on the PCB right here with a few little alignment holes. And that's it. No connector, no nothing. And just through press force, those connections are made. All right. Any other requests from the audience on parts to investigate? Maybe while we're waiting, I know we want to get to the trigger module, yeah, because we had a few requests for that. Would also love to get any other members from the audience come up on stage, and we can talk and go back and forth. So maybe we'll take a pause, and the man behind the curtain can convert us over into Q&A mode, so we can actually get some people up on stage. So this, for everyone else too, this will end the official recording, which will be sent out later, and the rest of it is just off the record casual talk. But there's lots more to tear down if you guys want to stick around and come up on stage.